Thank you very much. Yes, James Webb Space Telescope is 1 year old, hence JWST+1. I'll try and keep this to within 15 or 20 minutes. If anything piques your interest, all of this material, of course, is on the webbtelescope.org web pages. So let's go through what happened a long, long time ago. The Webb telescope was built. It was folded like a piece of origami, and then it was launched on Christmas Day last year. So within a few days, it has been in space for 1 year now. A reminder that the James Webb Space Telescope mirror is substantially larger than the Hubble's. You can see the comparison there. It's 2 to 3 times the diameter, so substantially larger in area. So it's going to be collecting a lot more light. Where is it working in terms of the wavelengths that it's going to be looking at? Here's the electromagnetic spectrum. We can ignore gamma rays on the left and radio waves on the right. It's this middle bit that's interesting. So the Hubble Space Telescope has been operating for the last 30 years or more, mainly in the ultraviolet and the visible, and just a little bit into the infrared to give us a taste of what was going to be coming with the James Webb. The Spitzer Space Telescope has been operational for quite a few years and is now retired as of a couple of years ago. The Spitzer Space Telescope operated in the far infrared, almost up to the microwaves. And as you can see here, the James Webb Space Telescope is occupying that gap. It covers the gap from what the Hubble covers to what the Spitzer used to cover. So then we've got a essentially complete part of that electromagnetic spectrum. So the James Webb is working in the infrared. And that's why it's been sent out to L2, one of the 5 Lagrange points where you can park a spacecraft and use essentially no fuel compared to putting it anywhere else in the solar system. So that red dot on the line joining the sun to the Earth and keep on going, that's the L2 point. That is where the James Webb is situated. The face of the Earth facing the sun, of course, is noon on that green line, and the face of the Earth facing away from the sun on the green line is midnight, local midnight. So you can think of it as the Webb as being effectively hovering 1 million miles above midnight, hence that particular expression. Why is it out there? It's out there so that its solar shield can block the light from the moon and the Earth and the sun and keep all the infrared detection and the mirror cold. Because it's working in the infrared, you can't allow any of these instruments to warm up. So that's why it's been placed at that location rather than the Hubble Space Telescope, which is simply orbiting a relatively shallow orbit around the Earth. So let's remind ourselves what the James Webb is supposed to do. One of its key aims is to look back in time as far as possible. Here's a reminder of what the universe has done since the Big Bang, kaboom, take that with a little bit of a pinch of salt. There's a kaboom 13.8 billion years ago, and here we have billions of years since then, and that's where we are now, 13.8 billion years later. The further the objects, the further the distance to the objects you're looking at, the further back in time you're looking, just because of the finite speed of light. It takes light a finite time to reach us if you're looking at objects that are billions of light years away. And we quantify how far back in time we are looking, given that we can't measure the time of a look back. What we can measure is how much has the light been stretched as it's gone from that distant object to us. Because the universe is expanding, as the light travels from distant objects to us, the light gets stretched. And the amount of stretch is what we call the redshift. And that's what these red numbers are. Redshift is indicated by a number called Z, and a Z of 0 means things close to us. A Z of 1 corresponds to objects that are some 10 billion years into our past. And the furthest you can go without using a telescope is about Z equals 4. So you can go back in time quite a few billion years to less than 2 billion years after the Big Bang, even without using a telescope, just using a camera to image very distant objects. But the reason Webb is there is because it wants to explore this region in the very, very left-hand corner. When were the first stars born? When were the first galaxies born? So Webb was built to look back into that very early universe. If we expand that out, what we've got is the Big Bang, and now we've got hundreds of millions of years. So how far back in time can we possibly go? Well, the Hubble Deep Field, which looked into the distance and tried to look as far back as possible, got to about here. a redshift of 10 corresponding to about 500 million years after the Big Bang. But already it saw that galaxies existed. Even at that early stage, galaxies were already formed and already evolving. So when exactly did galaxies form? Was it 400 million years after the Big Bang? 300? 200? We don't know. And the James Webb, looking in the infrared, because light is stretched more and more the further back in time we go, a lot of visible light has been stretched into the infrared. So the James Webb will be able to look back further. And it is hoped that the James Webb will be able to get back to perhaps 200 million years after the Big Bang. And the question arises, did stars exist at that time, or did they come into being sometime during this timeline? We don't actually know, because so far we've only got to a redshift of 10, corresponding to about 500 million years. I'm not going to talk through everything that's come out of the James Webb, because there's far too much and I've got far too little time. The first release images, you may have remembered these from back in June 2022. There was a big hoo-ha, a lot of media coverage, a huge amount of information on the news and other web pages, so I'm not going to talk through those. What's happened since the middle of the year? In July, they released images of Jupiter, and you can see that the resolution of Jupiter in infrared is very similar to the resolution of the Hubble images. The James Webb has got a bigger mirror, but if it's a bigger mirror working with longer wavelengths, you end up with a very similar resolution. So the detail is very similar. But it's interesting to note that if you look at the original images of Jupiter, not only do you see all of the detail in the belts and the north and south aurora, but if I just make that just a little bit brighter, you notice that as well as seeing the rings and moons of Jupiter, you even see galaxies in the background. You're taking a picture of a very bright object, but still, because of the sensitivity of the James Webb, you can see some galaxies in the background. That's pretty amazing. One of the things it's been doing is looking at large swathes of galaxies, not necessarily picking on one or two galaxies that are interesting, but a bit like the Hubble doing a deep field, look at a patch of sky and see how many interesting galaxies are out there. This at the top, which you can barely see, just peppered with lots of points of light, that is a mosaic of 690 images taken of a patch of sky to try and look at what's out there. And some of the blow-ups of some interesting galaxies are at the bottom there. One galaxy that's undergoing a lot of star formation, an interesting collection of galaxies that appear to be in an arc. This one is not part of the group, but still they'd like to understand why it is that galaxies seem to have formed almost in a straight line. This one is nice. It's either a footprint or a squid. This one has been named a Space Kraken, which I thought is a great name for a collection of interacting galaxies. So there's clearly a lot going on there that they need to study to try and work out what this galaxy is actually doing. This galaxy set is at a redshift of about 1, so it's not a long way down that line we were talking about to the early universe. It's only a few billion light years away. And here we have a couple of interacting galaxies, and you might not be able to see what the arrow's pointing at. The arrow is pointing to a little point of light. That is officially the first supernova that James Webb has seen. No other telescope saw this before James Webb took a picture of that galaxy and then realized there was a supernova going off as these two galaxies are interacting with each other. And if we blow that up, again, there's nothing particularly special about this galaxy, but this galaxy is billions of light years away, by no means one of our neighbors, and yet we can see structure. James Webb has the resolution, looking back in time for billions of years, to be able to see galaxies and see detail in those galaxies. They're not just tiny smudges, even though we're looking billions of light years. And this final picture, again, is just a reminder that whenever we look at any collection of galaxies, we have to be careful to make sure we understand, are they all in the same group? In this case, this one appears to be a foreground galaxy, and these ones are background galaxies. You can't really tell. Color is an indication, but you can't really tell until you've taken the spectrum of everything in the image, and then by looking at the redshift, you can work out the distances of lots of these objects. The background picture is not a Webb picture. The background picture is just to give you context. This is a chunk of sky. What Webb has done is image an exoplanet. Yes, this has been done by the Hubble Space Telescope previously, but here we see in much more detail an individual exoplanet going around another star. In this case, the star is hundreds of light years away, and by blanking out the star, the little five-pointed graphic of a star is where the star would be before it was digitally removed in order to show us what's going around that star, which turns out to be this particular planet, imaged in different wavelengths. And yes, there are some artifacts in some of these images, but you can quite clearly watch this thing. If you go back and take another picture of it, you'll be able to see this planet orbiting its star. And again, you'll be able to take spectra of these planets to see what's going on those planets. So it's not simply imaging to show they exist, it's imaging with the possibility of spectroscopy so we can understand better what these planets are doing. Here's a cartwheel galaxy. Again, the Webb has revisited quite a few objects that have already been imaged by Hubble. The cartwheel galaxy was imaged by the Hubble Space Telescope. This is a picture in the near infrared, and if we add in the mid-infrared, we can start to see there's an awful lot going on in this galaxy. Why does it appear to be a galaxy inside a big hoop? Well, they believe that one small galaxy, not necessarily within this image, a smaller galaxy has gone ploughing through this large one, and just like ripples in a pond, if you throw a stone into a pond, you leave ripples moving outwards. They think a galaxy has gone through close to the core of this one and has left ripples that are moving outwards, and the ripples, as they move outward, start to catalyze new star formation. So they're seeing lots of hydrogen and interesting hydrocarbon molecules in this galaxy because of a galaxy collision. And again, you can't tell that unless you do the spectroscopy. This is why the James Webb has got so many spectrographs on board. It's not just an imaging device, it needs to take spectra to understand what's going on. The Tarantula Nebula is a star-forming region within the Large Magellanic Cloud. Interesting because it's one of the closest that we can clearly see. A lot of star-forming regions within the Milky Way are obscured because of the plane of the Milky Way. But by looking in the Large Magellanic Cloud in the southern hemisphere, you get a really good close-up view of this particular star-forming region. So it's a big nebula, and you can see that this appears to have been excavated. It appears to have been hollowed out, and that's produced by the radiation of these bright blue stars in the middle. And if we zoom into one section and then zoom in again to a particular star, we see what's going on at different wavelengths which correspond to emission from different elements. So around a given star, again, this is 100,000 light years away, we can see what is the hydrogen doing, the atomic hydrogen. In other words, hydrogen where the individual atoms are floating around free. But next to that in green, what's the molecular hydrogen doing? Molecular hydrogen is two hydrogens bonded together, floating around in pairs rather than individually. Why should that make a difference? Who gives a damn about whether the hydrogen is an atom or a molecule? And there's also hydrocarbons in there as well. Well, the difference between hydrogen as an atom and hydrogen as a molecule is crucial to understand star formation. For a star to form, it needs to have molecular hydrogen. If there's only atomic hydrogen around, it's very difficult for a star to form, for reasons I'm not going to go into. And with the Webb, we can now see where is the atomic hydrogen, where is the molecular hydrogen, and we see there's a lot of molecular hydrogen within a bubble around the star, and that's why that star is forming in that particular location. A nice picture of Neptune with its rings and its moon Triton there. Triton, it looks very odd to have a moon that's outshining the planet. But the planet, unlike Jupiter and Saturn, which are mainly hydrogen and helium, the ice giants like Uranus and Neptune, they actually have quite a bit of heavier elements and heavier molecules in them, like methane, and that makes the planet a little dull. Whereas Triton, dull in the sense of brilliance, not interesting. Whereas Triton actually is covered in nitrogen, which reflects infrared, and so Triton looks amazingly bright in this same picture. In October 2022, we got this really weird image of a star which looks like it's got tree rings around it, but they figured they understood exactly what's going on there. Two stars are going around each other, and every time they get close, one tidally disrupts the other and pulls off a bit of material which then goes flying out. This happens every 8 years as they go round each other, and hence you get this effect of tree rings, effectively one ring for every 8 years. So we can time effectively how long this particular stellar system has been ejecting material. This particular star is thousands of light years away, but again, Webb has the sensitivity to pick up this sort of detail. And I hardly need tell you what this particular image is. It's just an incredible image. The pillars of creation were imaged in 1995 by the Hubble Space Telescope, and not surprisingly, the Webb has gone back to revisit to see what it can see. A different amount of detail, a similar resolution, but a different amount of detail, just because infrared doesn't get scattered by the dust in the same way that visible light does, and hence you can see more detail. I like that particular way of expressing it. The same image effectively, just rendered in a different color palette. This was released for Halloween just because they thought it looked a little bit ghostly, so that's a good one for the media to release around Halloween, as it looks like you've got a whole load of ghosts heading off into the distance. Looking a long way into the past, this is now a redshift of 3, so now we're looking 10 billion years into the past. They're looking at a quasar which Hubble showed as a dot, but when the Webb went there and looked again at different wavelengths corresponding to different speeds of things moving around this particular quasar, a very active core of a galaxy, what they found is that stuff is moving really fast there, much faster than they would expect, which means this thing must be much heavier than they expect. Even accounting for supermassive black holes and even accounting for dark matter, it came as a surprise. So they think this particular system is actually multiple galaxies really close to each other, orbiting each other quite quickly. Unlike what we're used to, where we are 1 million light years away from Andromeda, here these galaxies are very close to each other, producing these very high velocities when we look closely in detail. My time is limited, so I better get a move on. Here's a nice comparison of a galaxy that was imaged with James Webb and the same galaxy imaged with the Hubble Space Telescope. Makes 3 very useful points. One is the resolution is the same. If you pick out a particular bit of interest here and flick between the two, the amount of detail you can see in any particular object is roughly speaking the same. James Webb, bigger mirror, but bigger wavelengths. The other point is, if you look over here, for instance, at those galaxies, you notice that the galaxies are much brighter, the distant galaxies are much brighter in the James Webb. Again, we're talking about a universe which is expanding, so the wavelengths are being stretched, which means visible light is being moved into the infrared, and hence galaxies are brighter in the infrared. So if we again just jump backwards and forwards, the galaxies are brighter in the JWST. The other obvious difference is, if you look at the Hubble, you can't see what's going on where these two galaxies appear to be colliding because it's just too dusty, and you really don't see anything in the center. But the James Webb shows something very bright in the center of this galaxy pair. Not surprisingly, that's a supermassive black hole in which matter is falling in, producing a huge amount of radiation, and despite the fact that it's very bright, you don't see it in the Hubble just because the dust kills it dead and it doesn't allow that light to be released. So an interesting comparison of the same galaxy pair in James Webb and in the Hubble. We're now moving into November, so we're almost up to date. I think this is one of the most amazing pictures, the so-called fiery hourglass. What's going on here is a star is being born. This star is probably less than 100,000 years old. Not millions, not billions of years old, a few 100,000 perhaps. And this material is effectively falling in under gravity to produce a star. And the star is right in the center there where you can't really see it. And an accretion disk, matter is falling in and producing a ring of matter, trying to get into as close as it can to the central gravitating body, the protostar at the center there. So that little nick you can see in the waist is the accretion disk forming around the protostar. Maybe that's planets that ultimately will come into existence. But all of this matter up here is falling in, making the protostar. Blue corresponds to relatively thin amounts of gas and dust. Orange corresponds to rather thicker amounts of gas and dust. And as the material is falling in, that protostar is starting to light up, probably no nuclear fusion yet, but it's starting to light up, and light is coming out, not in the plane of the accretion disk, because that's too dense, but light is coming out, as it were, in the north and the south direction, lighting up the nebula in these two directions, giving you this sort of hourglass effect. So it's rather nice to look at, and there's an incredible amount of information in images like this when you couple it with the spectra of what you're looking at. I better move on. This is a galaxy cluster released in November, and now we're starting to push the redshift. Some of these galaxies, when you take a snapshot of the sky, some of these galaxies are redshift 10, redshift 11, redshift 12. We're now pushing beyond what Hubble could do effectively. So Hubble has imaged pretty much as it can in terms of the early universe. Webb is now taking over that mantle and is pushing the redshift further and further, looking further and further back in time. It's still only got to about redshift 12. There are some unconfirmed candidates which might be redshift 15 or 16 or 17, but they haven't been confirmed yet. Finally, let me finish with what it's been doing with exoplanets. The idea is if a planet moves in front of a star, the light dips, and whilst the planet is in front of the star, some of the light of the star will go through the planet's atmosphere. And hence you can do spectroscopy of what planets are made of. I'm not expecting you to read these things, I'm just showing you that lots of spectra have been taken of this particular system called WSP-96b, and as a result you can look at where these peaks occur as a function of wavelength, and you can determine that this planet, which is some 700 light years away or so, we know that its atmosphere has got sulfur dioxide, carbon monoxide, it's got sodium, it's got potassium. We know, and water vapor. So we know that this system has got clouds, and we know that this system has chemical reactions in the atmosphere, because we can tell that from the balance of molecules present. What hasn't been found is methane. They are looking always for methane, because if you can work out how much methane there is compared to oxygen-based molecules, you can work out a good probability of whether life exists. In the early Earth, we had a lot of methane when the first bacteria came along. And if we can see methane in exoplanets, that will be a very good sign that we're looking at life beyond the Earth. In this particular set of spectra, no methane. But this is very early days. This is one of the earliest systems that it's looked at. It hasn't yet done a proper study of the TRAPPIST system. It hasn't done a proper study of the thousands of exoplanets that Kepler has already found, for instance. So to date, we have no evidence of life beyond Earth. But it won't be long. It's only 6 months old as far as taking data is concerned. It got to L2 after a month, but it didn't cool down until about 6 months. So we're only getting data for the last 6 months, and hopefully it's got many, many years ahead of it. It will be looking at lots and lots and lots of exoplanets, looking at atmospheres, looking for life. So far, no signs of life beyond the Earth, but it won't be long. We don't know if life is really out there, and it doesn't really matter whether we're talking life like us or just other life. Maybe one day we'll see not only other life, maybe other Santas as well. Who knows? Thank you all very much.